Hey guys, my name is Z and you're watching Makes It Easy. And welcome to my IGCSE chemistry series where today we have topic 6, which is metal extraction or electrolysis. And here are the lessons that I'll be covering. They are ores, electrolysis, electrolysis of aqueous solution and part 2, electrolysis of brine, extraction of aluminium, blast furnace and alloys. So check out the pinned comment in the comment section for all the timestamps. But we'll move on to some basic facts here. We have like some diatomic elements, monatomic elements, and some information about the periodic table and some atomic number and mass number. And we'll move on to our first lesson, which is ores. So here we have increasing reactivity, like a reactivity series. We have above carbon, there's potassium, sodium, calcium, magnesium, and aluminium. And because of the high reactivity, the metals above carbon are extracted by electrolysis, and the metals below carbon are extracted by heating them with carbon in a blast furnace. And like let's say gold and platinum, some metals do not need to be extracted because they are so inert or unreactive. You find them on their own in the ground or in the soil. So here's increasing reactivity and the description. So into some information to have a read for a few seconds, then we'll move on to some questions. So here are more information. You can just come back to this like second to refer back. And here. So here are some questions for those key cards. So we have box 1 and box 2, the difference, which are right here. And then the questions. Looking at the difference between the substances, why might the substance in box 1 not need further chemical reactions carrying out on it, which is this one. And it's obviously because substance 1 is unreactive, gold, and it's already a pure metal. And why might the substance 2 need to undergo further chemical reactions in order to get the pure metal? And because substance in box 2 is an impure compound, and aluminium is highly reactive and it is reactive with oxygen, therefore it needs to be separated via chemical reactions to get pure metal. Number 3. Using the knowledge you've just gained, why might the substance in box 3 need to undergo further chemical reactions in order to get the pure metal? And we have here. Because substance in box 3 is a compound and it is impure as it contains 2 different types of elements, meaning it needs to be separated from oxygen to become pure. And here are more questions. Looking at the difference between the ores, explain why the high grade copper ore is more economically worthwhile to mine. So basically the diagram has a high grade copper ore and a low grade copper ore. And the higher grade copper ore has more copper oxide as there's a larger metal concentration of the desired mineral. So there's a larger copper metal concentration, or there's a higher percentage of copper. And therefore, why do you think copper ore 2 is called a high grade? And it's because it has a higher concentration of copper for mining, so it is economically worthwhile to mine. And when the ore has been mined, what do you think you will have to remove in order to get pure copper? And it is to undergo further chemical reactions to remove the oxygen. And then we have more analyzing graph questions you can read, using the graphs to solve questions. Like what percentage of metal compound needs to be in the ore in order for it to be economically worthwhile to mine it? So you can read. And above 52% is economically worthwhile to mine because if the metal compound is higher than 52% in ore, the money made from mining 1 kg of ore is higher than 500 pounds, which is the cost of mining 1 kg of ore. So the cost of mining 1 kg of ore is right here, and money made from this. So to be economically worthwhile, the money made from mining the ore has to be above the cost of mining, or else it will be negative profit. So it has to be above 500 pounds, so above around 52%. And describe the pattern shown in the graph, like using data or numbers from the graph to support your answers. And there's a positive relationship and a linear relationship between the percentage of metal compound in ore and money made from mining the ore. And the higher the percentage of metal compound in ore, and the more money made from mining 1 kg of the ore in pounds. Then we have some ores extracting metal questions. So here's metals less reactive than carbon can be produced by heating the metal compounds in the ore with carbon, which is called in the process in blast furnace. So number 1, what is ore? Ore is a mineral that has a valuable metal inside, and it has to be economically worthwhile to mine. As rock compounds and metals usually found in the earth, unreactive metals such as gold are found in the earth as a metal in itself, but most metals are found in compounds that require chemical reactions to extract the metal, such as copper oxide, and they are typically metal oxide. And how do you get iron out of its oxide, which is hematite? Iron can be extracted from hematite or Fe2O3 from a blast furnace, and carbon is also added in the blast furnace, and carbon monoxide will be produced to react, which we'll look into later. And carbon is also reacting with the oxygen. The oxygen is removed in the iron 3 oxide in order to leave the iron behind. And what is this type, the iron reaction called? It's called a reduction reaction and the displacement reaction. So we'll look into types of metal. We have high reactivity, which is above carbon. With the extraction process is electrolysis, like magnesium oxide and aluminium oxide. For middle reactivity, anything below carbon is reduction with carbon using blast furnace, like iron oxide or zinc oxide. And low reactivity, like gold or platinum, they are found in nature by itself via mining, like gold or silver. Then we'll move on to the different reactivity series. We have this normal reactivity series, like potassium, sodium, and silver gold. So these will be typically found by themselves. And here's blast furnace, and above carbon, electrolysis. And group 1 and group 7 you can read for the reactivity series. So we'll move on to some definitions for electrolysis. Oxidation is an ion loses electron or the addition of oxygen. Oxidizing agent is an agent that causes something to be oxidized. Reduction is an ion gaining electron and the removal of oxygen. And reducing agent is an agent that causes something to be reduced. And redox reaction is a reaction where an ion gains oxygen and another ion loses oxygen, which redox is a reduction of oxidation happening at the same time. And oil rig stands for oxidation is lost and reduction is gained. So look more into the oil rig. So oil, gaining oxygen, loss of electrons, oil, and they are reducing agent. And reduction, loss in oxygen, gain of electrons, rig, or they are oxidizing agent. So here are some examples. We have copper ion plus 2E minus, 2 electrons to become copper atom. Iron 2 plus ion to plus minus 1 electron to become Fe3 plus, and these. So one simple thing to know how to write this it's called half ionic equation, is that if you want to have an ion to turn into an atom, just see what charge there is for the ion. So here we have copper 2 plus, so it will plus 2 electrons. So if it's copper 3 plus, it will plus 3 electrons. Copper 4 plus, plus 4 electrons. And if it's copper 2 minus, then minus 2 electrons. It's the same sign. Then we'll move on to some bondings. So here are the basic 3 types of bonding. There's ionic bonding, which is transferring electrons. Covalent bonding, where they are sharing electrons, and metallic bonding, where delocalized electrons move freely between adjacent metal ions in the solid state. So ionic bonding is an electrostatic attraction between two oppositely charged ions. Covalent bonding is strong electrostatic attraction between a shared pair of electrons and the nuclei of the bonded atoms. And metallic bonding is an electrostatic attraction between the delocalized electrons and the positive metal ions arranged in the lattice. And then we'll move on to more ionic bonding. State the structure of sodium chloride and explain why it has a high melting point. So just talk about these points over here, or the bolded points. They have an ionic lattice structure and high melting point because many strong electrostatic attraction between oppositely charged ions, and that's why it requires a lot of energy to break the bonds or overcome the forces. So high melting point. So I'm sure we all know from the previous topics that ionic substances do not have free electrons, but they can conduct electricity if they are liquid or gas because they are free moving ions. Then here's more on the lattice. Here's how lattice can be broken up in 3 ways. There's the physical stress, where you apply force, dissolving it in the water to become aqueous, and heating it so that ion particles get heated up, and when they have enough energy they break the bonds and move freely and become gas. and this process of heating is called endothermic reaction because you're taking in the heat. But we'll focus more on endothermic and exothermic in energetics in the coming topics. Then we have electrolysis. Electrolysis is a chemical decomposition produced by passing an electric current through a liquid or solution containing ions, and the ions need to be free moving. And you see, these are electrodes. You see these colored things. And in carbon or graphite, specifically electrodes, is added to the electrodes because graphite can conduct electricity, and carbon is inert, so it won't react. Because you know that carbon is 4 plus bond and 4 plus charge, so it can share 4 electrons. But in graphite, the carbons only share 3 electrons with each other. It means that for every carbon, there's 1 free moving electron or delocalized electrons, so that's why they can there's free moving electrons. So in the positive side, oil happens, or oxidation is lost, oxidation happens. In the negative side, the break happens. So we'll look more into positive and negative. And when a soluble ionic compound dissolves in water, the lattice breaks up, and the ions separate and are free to move around rapidly, and the ions can carry electrical charge through the solution. The solution therefore conducts electricity. So here's an extension. Water is made out of covalent molecules. Does it conduct, and why is it not safe to have it near electrical equipment? And the answer is water does not conduct electricity because it is covalent bonded, and it needs to have a charged ion dissolved in it. And it is not safe to have water near electrical equipment because it will have impurities dissolved in it, making water able to conduct electricity. So here's more on graphite. There are the intramolecular forces or covalent forces and the intermolecular. And we'll focus more on the conductive. Conductive because only 3 carbon electrons are used for bonding, and the 4th one is delocalized or free moving. So we'll move into some key terms. We have an electrolysis setup over here. We have this, which is splitting up compounds using electricity for the definitions for electrolysis. And these are the electrons, and they are rods that conduct electricity, and they come in pairs, and one's negative and one's positive. And this thing right here, the solution, it's called electrolyte, and they are ionic liquids or solution broken down by electrolysis. And these are more opposite attracts information. Negative ions move to the positive electrode like chloride, and electrodes, which are rod that conducts electricity, often made of graphite or platinum as they are inert, and positive ions move to the negative electrodes, which are copper. So here's panic. Panic stands for positive is anode and negative is cathode. However, positive ion is called cation, or because cat is happy. Negative ion is called anion. So one way to remember what the name for the electrodes are is that think of positive ion, it's called cation, and cation is like positive ion is attracted to negative electrode, and negative electrode have the same name as the positive ion, cat. So negative is called cathode, and positive is called anode, because it's attracted to the negative ion called anion. So it's basically the opposite, positive and negative. And here's the setup over here: the electrolyte, ions, the anion, and the cathode, cation. So we'll move on to electrolysis of lead to bromide. I'll just play this video as I talk about it. And an ionic compound, lead bromide, can be split into its separate ions. Can be split into its separate ions, which is Pb2 2 plus and Br minus using electricity, and we call this process electrolysis. The electrodes are placed into a solution containing lead bromide, and the negative ions move the positive electrodes, which is called the anode. And here, the bromide ions give up their electrons to become bromine atom. And the electrons that were given up travel to the cathode, making it negatively charged. These electrons are then given up to the Pb2 plus ions, which are then turned into lead atoms. And the bromide will be seen as an orange gas, and the cathode will eventually get heavier due to the formation of lead, Pb. And here's in the anode where oxidation happens. There's two Br minus 2 E minus electrons. They will become bromine gas, and it's group 7 halogens, so it's diatomic. So you need 2 electrons and 2 bromide ions. And for cathode, it's a reduction reaction where Pb2 plus 2 electrons to become Pb solid. And here's the equations, the ionic equation. So we'll move on now to anode versus cathode. You can have a look at the salt right here. And here's what happens in each of the anode and cathode, like potassium bromide. In the anode, it will be bromide ion forms bromine, and in the cathode is potassium cation. You can see. And anode, the process is called oxidation, so it's the loss of electrons. So you can see they're all loss of electrons. And cathode, where it's reduction, the gain of electrons. So we'll move on to some questions for electrolysis. Why do salts like sodium chloride crystals not conduct electricity? Because all the atoms and ions in the sodium chloride ionic lattice in the solid form have a fixed position, so they can't move around. And give two ways to make salt conduct. You can either melt the salt to become molten form or dissolve it in the fluid or water. And does the solution of C12H22O11 conduct electricity? And explain your answer. And the answer is no, because there's no free moving ions due to the sugar having covalent bonds instead of ionic bonds. So there's no free moving ions. Then we'll move on now to electrolysis of aqueous solution. What is an electrolyte? And it's an ionic liquid that has been broken down by electrolysis. And why do ionic substances need to be molten or dissolved? And the answer is so that there's free moving ions. And what ions are attracted to the negative cathode? And it's cation, the same name. What happens at the anode? An ion is attracted to the positive anode, and in the process called oxidation, because anodes lose electrons. And what is the difference between an anion and cation? An anion is negatively charged ion, and cation is positively charged ion. And what would you observe during the electrolysis of lead bromide? And in the cathode, bubble is given off, and in the anode, the color will change and the mass will increase due to the formation of Pb, the lead. Then we have a diagram. We have electrolysis, the electrodes, and here we actually have an ammeter, which is used to measure the current. An ammeter is to measure the current, which is the amount of electrons passing per second flowing through the circuit. And ammeter is added to determine the rate of reaction in which it is happening. And this also proves that electrolysis is happening when we get a reading, because it means that there's electrons flowing from here, which proves that electrolysis is happening. Then we'll move on to electrolysis of aqueous solution. We have a diagram right here. Hydrogen and copper ions are attracted to the cathode, and copper is being discharged because a brown solid is formed over to the left. And if hydrogen were to discharge, we will observe fizzing or effervescence. And sulfate ions and hydroxide ions are attracted to the anode. And oxygen gas is being formed, meaning oxygen is discharged. And universal indicator will turn red because H2SO4 is formed in the solution. Because we know that copper is being discharged due to preferential discharge, where we'll do it later. So copper is being discharged and oxygen is being discharged. So what's left is hydrogen ions and sulfate ions, and they react together in the electrolyte to form H2SO4, sulfurous acid, so it becomes as acidic. So universal indicator will turn red. So we'll move on to some strong acids. We have hydrochloric acid, sulfurous acid, and nitric acid. They are strong acids because they dissociate their ions easily while dissolved in water. Because the anion that the acid contains is more stable and they are one electron less or more in the outer shell. So this is quite a complicated one, so we wouldn't be able to required to know this in IGCSE. But we'll move on to our next content, which is electrolysis again. After compounds have been split into its ions and they reach the electrode, they turn back into atoms as they gain or lose electrons. This is because the ions, as I talked about just now, gain or lose. And SO4 loses 3 electrons to turn into atom, like you can see here, -2, C plus for copper, so it will be reduced as it's +2. OH-, we'll look into it later here. And here, hydrogen ion to gain 1. So for the discharge or the OH hydroxide ions to lose electrons, we will have this differential discharge, oxygen gas will form in the positive electrode or the anode. And for the preferential discharge for hydroxide ions, we have 4 OH minus, minus 4 A minus electrons to become oxygen gas and water. So it's a different one from the rest of the discharge series. And 2 hydrogen ions must come together before hydrogen atoms are formed because hydrogen is diatomic, as well as H, hydrogen, nitrogen, oxygen, and group 7 halogens, as I talked about in the first slide. So we'll move on to preferential discharge. The preferential discharge is based on the reactivity series, and the relatively least reactive ions are preferentially discharged as elements. And you can have a read for the cathode and anode. So here are some questions. What is discharge in preference to Zn zinc ion and its hydrogen ion? What is discharge in preference to SO4 and its hydroxide ions? And what 2 gases are produced in the electrolysis of copper sulfate? And they are oxygen and hydrogen. So if you're a bit confused, you can have a look at this table right here, the preferential discharge series. We have the cations and anions. Here's easy to discharge and hard to discharge. So you can actually, if you look closely at the relationship, you can see that it's the inverse of the reactivity series. At AU, gold right here, it's the easiest to discharge, but it's the most least reactive in the reactivity series. And because over here, gold is the easiest to discharge because it is the most unreactive element. Therefore, it wants to exist in an atom form and not in ion form. So it wants to do anything like gaining electrons to become an atom, and so it would be discharged. So for cations, the high electropositive increases as you go down, and it means we'll lose electrons, and high electronegative will attract electrons. So we'll look into extended for CuSO4 copper sulfate. The copper ions from the solution migrate to the cathode and can be seen to deposit. And the 4 ions involved in the CuSO4 are, of course, copper ions, hydrogen ions, sulfate ions, and hydroxide ions. So you can have a read for the cathode and anode. So we'll move on to some questions. The compounds, state, and ions. Compounds include potassium chloride, which the state is, if it's molten, that means it only contains potassium and chloride ions, chlorine ions, so the cathode and anode. Aluminium oxide, if its state is molten, ions and discharged. Compound state, and all of these are solutions, so it's aqueous, so it contains hydrogen ion and hydroxide ion. And what will be discharged are as follows. So this will be hydrogen because hydrogen is will be preferential, because hydrogen ion will be preferentially discharged than sodium ions. And oxygen as well, So we'll move on now to explaining electrolysis of NaCl, and I'll just briefly go through this as we talked about it just now already. So electrolysis is a chemical decomposition produced by passing an electric current through a liquid or solid containing ions. A brine is a high concentration of salt, like in water, like sodium chloride, table salt. Electrolyte is an ionic liquid or solution broken down by electrolysis. Electrodes are an electrical conductor rod that conducts electricity, and it is often made of graphite because it is inert and but still conducts electricity. And cathodes are negatively charged electrode, and cation is positively charged ion. And anode is positively charged electrode, and anion is negatively charged ion. So here's diagrams, and we'll move on to some conditions. Here are some conditions of substances that are needed to be able to undergo electrolysis. They need to be able to dissolve in the liquid, and it needs to be molten so that there's free moving ions. So as I talked about just now, the ionic compounds have to be either molten or in aqueous solution so that they have free moving ions. And ionic bonding over here, the electrostatic attraction between oppositely charged ions. And an ionic lattice right here, or as we call in year 9, the giant ionic lattice structure. So we'll move on to more closer look at the ions. Oxygen and hydrogen atoms are covalently bonded in water, and oxygen, which are 2 plus 2 minus charge atom, attracts electrons a bit more strongly than hydrogen 1 plus charge does. This forms an unequal sharing of electrons. Therefore, it gives a water molecule a slight negative charge near oxygen and a slight positive charge near hydrogen, meaning water is polar and they are covalently bonded. And we'll touch onto this in A-level chemistry and not IGCSE chemistry. And how can NaCl lattice be broken up? And as I talked about in the first few slides, you can have a read, dissolve, and you can have a read of what happens when it dissolves. And positive ions get surrounded by the water by the negative side of the water, oxygen, and the hydrogen in the other side. And then we'll move on to the electrolysis. And electrolysis, as we talked about, is an electrochemical reaction. An electrochemical is a process caused by having an electric current and involving the transfer of 2 electrons or electrons between 2 substances. And here you can see the setup. And electrons moving from positive charge anode to negatively charged cathode. So we'll move on to some observations. And in this electrode right here, the anode, chlorine gas will be discharged and we will observe bubbles coming out and fizzing or effervescence. And in the cathode, hydrogen gas will be discharged and we will observe the same, bubbles coming out and fizzing or effervescence. And to confirm that what gas is which one, we can carry out the test. The anode, which is chlorine gas, we can put damp blue litmus paper and it will turn red, then bleaches due to the formation of hydrochloric acid with water, and then hypochlorous acid, which bleaches it. And in the cathode, we can carry out the pop test for hydrogen, the squeaky pop test. And we'll move on to the preferential discharge as I talked about just now. Just skim through this. We have the H plus right here and the Cl minus. And you can see OH right here, it's below chloride ions, so chlorine will be discharged. And you can see hydrogen right here will be preferentially discharged because Na, which is the other ion, the other ions, is right down here. So we'll move on to some explanation. You can see salt, state, ions present, anode and cathode in some formulas or equations. Then we'll move on to extraction of aluminium. Here's the equation for decomposition of aluminium oxide. We have 2Al2O3 to turn into Al plus oxygen. And here's the learning objectives. Then we'll move on to the extraction questions. I'll just play this video while I'll just talk through it. And yep. What process is used to extract aluminium? And it's extracting from its oxide by electrolysis because it's above carbon. And what is aluminium oxide often called? It's called alumina or bauxite. And where does the ore come from? And it's imported from Jamaica, Ireland, Spain, where it's purified from bauxite ore. And what is the name of the impure ore? They're called bauxite ore, and this bauxite is purified to yield a white powder or aluminium oxide, also known as alumina, from which aluminium can be extracted. And bauxite is primarily comprised of aluminium oxide compounds or alumina, silica or silicon, iron oxides, and titanium dioxide. And what current is needed at the plant? And rows of electrolysis cells are called pot line, and it requires 157,000 amps or and 4.5 volts. And what is alumina dissolved in molten cryolite? So that the alumina conducts electricity. Cryolite, or this equation right here, also lowers the boiling point of alumina, or cryolite also lowers the boiling point of the whole molten solution. And you can see. And this right here, the wording is a bit not correct, because we can't say cryolite lowers the boiling point of alumina or aluminium, because it technically doesn't. The cryolite lowers the boiling point of the whole molten solution. Because beware is that in some tests or like mark scheme on paper, if you say cryolite lowers the boiling point of aluminium, you're marked as incorrect, because you have to say the solution or the molten whole solution. And which electrode do the oxide ions go? Because they are negatively charged, so they're attracted to the anode. And then we have some more details for the extraction for aluminium. We have this electrolysis right here, which is quite strange. We have two positive electrodes and a negative electrode. And the steel case used in electrolysis is coated by graphite, and graphite is a form of carbon and X at the negative cathode. And aluminium ions from the aluminium oxides are formed at the negative cathode over here, and they sink to the bottom because they are heavier than the cryolite solution. Then the aluminium that has sunk to the bottom is then collected in liquid form right here. And here's the equations. And we have to replace the graphite anode, or else oxygen will react with the carbon or the graphite to form carbon dioxide, or more dangerously carbon monoxide. And the use of molten cryolite as a solvent reduces some of the energy costs involving in extracting aluminium by allowing the ions in aluminium oxide to move freely at a lower temperature. And aluminium oxides need to be in molten form to extract the aluminium ions. Aluminium oxide, however, has a melting point of 2000 degrees Celsius. Therefore, aluminium oxide is dissolved in molten cryolite, and cryolite is a form of aluminium compound that has a lower melting point than aluminium oxide, so it lowers the whole molten solution. Then we have some extraction of aluminium. Aluminium is a very reactive metal as it is near the top of the reactivity series. So it is found combined with other elements like oxygen in the aluminum oxide in the bauxite ore. And we need to use electrolysis. And aluminium oxide or alumina is dissolved in cryolite to lower the melting point of the whole solution or the molten solution. And it's electrolyzed or decomposed. And electrodes are made of graphite because it is unreactive and inert but still conducts electricity. And the current of 147,000 amps is passed through the circuit. And the negatively charged electrode or cathode is located in the bottom of the whole setup, as it attracts the positively charged ion, which is aluminium. And the positively charged electrodes or anode are located on the top of the setup, attracting the negatively charged ions, which is the oxide ions. And we have to keep changing the positively charged electrodes or anode so that the oxygen doesn't react with the graphite or the carbon in the electrode to form harmful gases. Then we'll move on to electrolysis of ionic compounds. We can just have a read of the molten substance, formula, ions contained, and make sure it's molten, so it only contains those two. And equations and products for the different electrodes. So we'll move into steel starter for blast furnace. How is steel formed? Iron ore or hematite is first mined from the ground. It is then smelted in blast furnace where impurities are removed via limestone and carbon is added. And why is carbon added? And this carbon is added to iron to make steel stronger and harder and resistant to corrosion or rusting. And here's blast furnace steps. And number 1, at the bottom of a furnace, the coke or a fuel that has a high carbon content burns in the hot air blast to form carbon dioxide, and this reaction is exothermic. The heat release helps to heat the furnace, and here's a respective equation. And the carbon dioxide reacts with the coke to form carbon monoxide, and the carbon monoxide reduces the iron-free oxide to iron. And alternatively, in the hotter parts of the furnace, carbon reduces iron oxide directly, right here, so these two could happen. And the heat from the furnace decomposes the limestone, and it's endothermic as it requires heat to break the bonds. So limestone to carbon dioxide plus CaO, calcium oxide. And the calcium oxide reacts with the silicon oxide to form slag of calcium silicate, right here. So we'll move on to some information. I'll just skim through it. And as we know that the main ore of iron is hematite, and we extract iron by reduction of iron-free oxide with carbon. And raw materials for making irons are hematite, coke, limestone, and air. And these enter that the hopper will look into later. And hematite, coke, and limestone are added at the top of the furnace, and a strong current of hot air is blown into the bottom of the furnace, and that's why it's called blast furnace. And the temperature of the hot air is between 550 degrees Celsius to 850. And at the bottom of the furnace, the coke burns in the hot air blast to form carbon dioxide, and this reaction is exothermic, and the heat helps to heat the furnace. And the main reductant in the blast furnace is carbon monoxide, as it reduces with the Fe2O3. And in some parts of the hot blast furnace, the carbon also reduces iron 3 oxide directly. And the temperatures in the blast furnace ranges from 1500 degrees at the bottom, where the air enters, to 250 degrees at the top. And the hot waste gas exiting from the top of the furnace are used to heat the air going into the furnace, thus reducing energy costs. So energy cost is quite an important factor. And the iron flows to the bottom of the furnace and is removed from time to time as a liquid, and it flows into the molds as it is left to solidify. And hematite contains sand or silicon oxide as a major impurity. So limestone, over here, helps to remove most of the impurities in the form of slag. And the liquid slag runs down and forms a layer on top of the liquid iron because it has a lower density than iron. And the slag is run off, and the solid slag is used as a building material, particularly in road building. So here's more in the diagram. We have the cellar over here. Hot air in, hot air out, hematite, limestone in. And here on top we have the slag or calcium silicate and the molten iron. So here's a colored diagram. Then we'll move on to the reactants and functions. We have the function of coke, which is to react with oxygen to form carbon monoxide, or as a reducing agent to remove iron from an iron oxide directly if the temperature is high enough. And limestone is to react with sand or silicon oxide to form slag or calcium silicate to remove impurities. And carbon monoxide is a main reductant as it reacts with iron oxide and reduces it to form iron and carbon dioxide. And then we have plenary. Iron is the second most common element on the Earth's crust, and the main ore is hematite. And we extract iron by the reduction of the iron 3 oxide with carbon. And the raw materials are hematite, coke, limestone, and air. And the hematite, coke, limestone, and air are added at the top of the furnace, and the strong current of hot air is blown in the bottom, and that's why it's called a blast furnace. And as we talk about, the temperature ranges from 550 degrees to 850 degrees. And this is high enough to react with the coke, and the main reductant in the blast furnace is carbon monoxide. But in some parts, the blast furnace is hot enough to just react carbon with the Fe2O3. And the temperature in the blast furnace ranges from this in the bottom and this to the top. Then we have alloys at last. All the atoms in pure metals are exactly the same. This is because all pure metals are elements, and these atoms are all the same size and shapes. And an alloy is a mixture of two different types of metals. One thing to note is a mixture, and brass is a mixture of copper and zinc. This means that there are two or more different types of atom in an alloy, and these different atoms are different sizes. And to test is something to test, or like to the theory behind it, of malleable, is that if you push it and the layers shifted, there's no repulsion because the delocalized electrons are still holding up the ions. So that's why metals can be easily be like bended, or that's why I call it malleable. So here's more on the alloys. Because there are different sized atoms in an alloy, it is not as easy to push one row of atoms over another. This means that the alloys will be harder and more difficult to bend than pure metals. You can see like different sizes. Therefore, the alloy is less dense than the metal because alloys has large particles, so it can't pack closely. So it's less dense. Like you can see here, pure metal, alloy. So we'll look into metallic bonding, and metallic bonding is an electrostatic attraction between delocalized electrons and its positively charged metal ions. And here's a diagram right here, and the properties of metal. And they have high melting point because of these points, and they are malleable because of these points. And then lastly, we'll look into steel. Here are different types of steel. We have high carbon steel, metals present, and the carbon content, uses and properties. Low carbon, and stainless steel, which contains 0.1%, as I'm sure we all know what stainless steels are. Metals present, the uses and properties. Then we'll move on to information. The expected results of the test that are the alloy is clearly harder and scratches the lead, and the lead does not leave a mark on the alloy if we were to scratch it from one another. And the density of the alloy should be less than of lead because it's more loosely packed in alloy. And you could get the students to weigh the alloy and work out its volume by displacement and use the formula of density equals mass over volume to find the density of each alloy and the lead. And the lead will melt first, followed by the tin, and the alloy has the highest melting point because there's more attraction, and demonstrating clearly with very different properties from its constituent metals. Then lastly, we have matching. We have different alloys, what it's made from, and its uses. Aluminium alloy, it's made out of aluminium and magnesium and it's for air industry. Brass for copper and zinc for musical instruments. Solder with lead and tin and to join parts of electrical circuit. Gold alloy, gold and copper for jewelry. Titanium alloy, titanium, aluminium and vanadium for replacement joints. Bronze for copper and usually tin for the sculptures or ships' propellers. And lastly, steel for which is made out of iron and carbon, which is used to make car bodies. So the alloys colored in bolded, like black, those darker ones, are the ones that are more important in IGCSE chemistry as it will be assessed on. And that's it for this topic of IGCSE chemistry of metal extraction and electrolysis. And I hope you guys have enjoyed this, and if you did, please leave a like and subscribe and comment down below if you have any questions or criticisms. And check out my Instagram in the description to follow me for more daily content, and I'll really appreciate it. And that's it for this video, and I hope you guys have enjoyed this, and I'll see you guys in the next video. Until then, stay safe and happy learning.